Hi everyone, this is the next lesson in the sequence. This is using radioactivity. We know all about it. Now let's have a look about how we use it and where its applications are. You'll need something to write with, scribble with, jot down some questions and some key points. I'll have set and sent out diagrams that go with it. So if you've got a printer, if you're fortunate enough to have that, you could use them, or you could actually just cut and paste and your own notes for that. And also follow-up worksheets have been sent out as well. So plenty for you to be busy with during and after this lesson, and opportunities to pause at certain stages. Now, in terms of using radioactivity, we need to know how it's used in a variety of contexts. Sterilising surgical equipment, irradiating food, smoke alarms and leak detection, with a couple of others thrown in as well, and describe how it's used in tracing and thickness gauging in industry. So radioactivity, we know a bit about it, but it does have quite a few uses in the real world as well. So let's have a look at those. First of all, though, something that's not used for anymore is some sort of beauty cream, as it clearly was at some stage in the past. It looks a bit 1920s to me, but Cream Scientific, curative and I don't know, something make it look beautiful. But Thoradia, base of thorium, it's a radioisotope, and radium in a formula of Dr. Alfred Curie. Now, Pierre and Marie Curie were the ones who did the radiation, so it looks like they found somebody with a similar name and claiming it's got great benefits and science is great. But these days we don't go and put radioactive materials on our skin because it's dangerous. However, somewhere in your house you should have some americium 241, and you might immediately think, I know where it is. But if you don't, then you're not committing a crime, but you need to have some in your house, I would say. So if you haven't got one, something with contains americium, an alpha emitter, then I'd suggest you perhaps find out why you haven't got one, because it will be useful to have. Okay, key things then. Students often mix up the idea of irradiated and radioactive, which is really important that you don't do that one, because irradiated things have been exposed to ionizing radiation. They've had radiation falling upon them or landing on them, if it's alpha, beta, gamma, but they're not actually radioactive. They have been exposed to it, but they're not necessarily radioactive. So there's two key things not to mix up there. In terms of uses, we use radiation for sterilisation. There's a nice picture of strawberries, which currently is quite seasonable, I suppose. They used gamma rays. They used to kill bacteria, mould, insects, I suppose microorganisms we should say there, in food. Okay, and it can be done after the food's been packaged. So if you think about it, you put your food, think your strawberries come in and pun it with probably a bit of cling film over the top of them. You can actually irradiate them and sterilise them after that. It may affect the taste of this fruit, some people claim, but obviously supermarkets like that because it lengthens the shelf life. They don't go off, so there's less wastage and more profit for the supermarkets. Also, from a medical point of view, in physics, nuclear physics has great applications to medicine, but it can also be used to sterilise medical equipment. Obviously, if you're undergoing surgery or someone's performing surgery, you want sterile equipment to keep the patient safe. So obviously gamma rays again can be used to kill bacteria on medical equipment, and sometimes that medical equipment has to be plastic. In the old days they used to boil it all up in a steam pressure cooker for quite some time, and obviously that will kill all the microbes, but obviously then you have to get it out of the packet, leave it on the side of the operating table till you need it, and with the risk of airborne microorganisms landing on it. And often if things are plastic, well, they wouldn't really take to great heat for sterilisation that way. So gamma rays to irradiate these medical instruments, and also irradiating food that can go off. There's an example of a couple of sterile syringes by the look of it, but again they can be irradiated inside their container. They can be sealed first and then irradiated. How it's done, really, basically some sort of conveyor belt, whether they're wrapped or unwrapped, pass them through a gamma source, irradiate them for a set period of time, and out they come sterilised. Have a think to yourself why it can be done. Why can it be done with gamma rays when it's already in its package, and why is that therefore very useful, especially when you do medical equipment. You sort of rip it open, the packet, and immediately before you need it, so it's going to be sterile right till its point of use. So have a think about that and be able to answer questions on that one. Here's a nice picture taken this from the textbook. These strawberries, same length of time. They've been around on the shelf for a certain amount of time, but I suggest there's only one set that you wouldn't mind eating, because the ones on the left have actually been irradiated. And irradiated food, a variety of fresh foods can be irradiated to prolong their shelf life, means they don't go off so quickly. And obviously, you know, I remember when that first came out and it was all over the press, it was like, oh no, radioactive food, because people were confusing irradiated and radioactive, and like non-scientific people worry about this. You know, they see the label and they think, oh, the food's been, you know, it's radioactive, but it is not really. It's just been irradiated, and of course we know better, and you could experiment to see whether it's been taste any different or not with that one. So in terms of, you know, can you explain what irradiated means? And can you explain examples of where irradiation is used? And then perhaps go on to sort of jot something down about, you know, what are the advantages and disadvantages? And, you know, public opinion isn't scientific, but, you know, that could be a factor in how people use these. An exam style question linking to this might be this. So explain how radiation can be used to preserve food. Discuss arguments for and against in your answer. Your answer must explain why gamma source is used and not alpha or beta. Okay, so pause the video, have a think about it, or rewind it a bit, and see if you can write a response to that. So pause the video, be back when you're ready. Okay, hopefully you've done that, and you're now ready for the answer. So we would say that food is exposed to gamma rays, tells us that. 4 positives, it kills the bacteria or microbes in food. It can be stored for longer before going off, so there's less waste and more profit for supermarkets. You know, obviously they're in business. It kills pests such as insects that might be in food as well. You know, if something's burrowed into the food, the radiation will also do for that as well. Against public acceptance, public aren't that keen, or, you know, through the misconception about irradiation and radioactivity, the perceived risks or the danger that the food might have actually deteriorated, might be going half off before it was treated. So the toxins might have been produced by microorganisms. And also, in the final thing, why do we choose gamma? Because alpha and beta particles are too ionizing, and also alpha might not travel the distance to get there, and beta particles not suitable either, but we'll see a use of them later. So we use gamma for that, penetrating for that. As you go through this and think about it, you know, you need to ask yourself, why is that the particular best type of radiation to use? Knowing the properties that, as we do for alpha, beta, gamma, you know, why is it that particular type of radiation is appropriate in the use that it has? And obviously, if you ever get an answer on this that you have to write, you have to justify why. Why is that the one to use, as we saw with gamma for irradiation? Another important use of this is leak detection in pipes. If you've got a pipe underground, it costs a lot of money to dig up the road. You've all seen it happening, the inconvenience it causes and the expense and the number of people involved. So if you can detect leaks in a pipe through another method, you just know exactly where to dig instead of digging up the whole road. So what will you do in a pipe where you suspect a leak, and obviously not in drinking water, but other pipes that are underground, you know, your flow of water, if you contain a gamma source, and again we know gamma has, you know, a lot of penetration, travels a long distance, very difficult to stop and absorb. If there's a leak in the pipe, that gamma source will actually sort of be leaked into the soil, and if you pass a Geiger Müller tube over that, it will detect a higher activity rate in the area where the leak is. So you simply dig in that point there. Leak detection in pipes, but again, obviously not anything people are going to drink. There you go, as another example of the same things for underground pipes. Isotopes need a short half-life. Okay, so it doesn't become a long-term problem. You inject something with a half-life of maybe a few hours would be fine. You don't want something with 5,000 years in there, because it'll be around forever, effectively, and you wouldn't want that. But you can use short half-life materials to detect your leaks, dig up the road, get it all fixed, and then the half-life, it will decay away to save proportions for that one. But again, it must be a gamma emitter, so it can detect through any metal and earth where the pipe leaks. Okay, it's no good having alpha and beta. Alpha would be absorbed by the soil, and beta wouldn't pass through the soil either, but gamma, as we know, can do. Exam style question on this topic. Gamma source can be detected. There's a similar diagram. Explain what properties a radioactive tracer used to detect leaks should have. What drawbacks might there be of using such a tracer? So for 4 marks, guess what? Pause the video, see if you can write down an answer or jot down some bullet points about that for 4 marks, remember, and then pause the video, do that, and then come back when you've done it. Okay? Hopefully you're ready then for a model answer that would answer this question. Okay, and we're looking for things like that. We need a short half-life for this, so the radiation reduces. So a half-life of, you know, hours. Gamma emitter, it must be a gamma emitter, so it can actually pass to the detector through the ground. Alpha beta wouldn't penetrate the soil. a low activity level, so it doesn't actually damage any living things. And the drawback is it increases the background count. Obviously, it is introducing some nuclear radiation into the atmosphere and into the environment. But again, we manage those by low activity and short half-life for that one. In engineering and manufacturing, there are several uses, several very important uses of radioactivity in checking things. And if you look at this guy here, is welding something. Welding's a method of joining metals. If you do design technology, you know about this probably. But you join metals with welding, and often, it could be part of a high-pressure system. You might be welding pipes together that carry high-pressure steam or gas or something flammable or something, under pressure. And if there's any cracks or flaws in the weld, then obviously that could be very serious. It could leak or even burst and cause big problems. So in order to check welding, we can use radiation for that one, and it's sort of like detecting cracks. It's called crack detection as its field. And we can, again, our old friend gamma rays can be used in this to detect cracks in an object after it's been welded. Typically we're dealing with metal, fairly thin metal, and hence that's the reason why we use gamma rays. Alpha and beta wouldn't be any good because they wouldn't really penetrate that at all. So gamma rays, a bit like X-rays, you can use X-rays for this as well, but gamma rays does it as well. If you irradiate with your gamma rays a pipe, and if there's a flaw, some cracks in the weld, let's say, or flaws in the weld, and you wrap your photographic film around it, where there's cracks in the weld, you'll have a higher incidence of the gamma rays passing through, and therefore it'll be brighter on the photographic film that you develop. You can have detectors as well to do that now, but in the old sort of schools, that photographic film wrapped around it, irradiate it with gamma rays, and you get exposure and affected where there is a crack because more gamma passes through, as you can see from this diagram here. And that's called a form of quality control in manufacturing. You want to see if it's good enough to withstand the job it's supposed to do. So it would appear under the sort of quality control heading is using gamma rays to detect cracks, particularly in welds. Another important use, and one that crops up fairly regularly on exam questions in the past, is rolling mills. Okay, whereas you need a material that has to be a certain thickness and it comes out as sheets like paper, aluminium baking foil, or sheet steel. If it's thin sheet steel, we need to make sure that's the right thickness, otherwise it's too thin, too thick, it's no good for its job, or we're wasting material by putting too much in there. And we use a machine a bit like this, where we've got rollers, which obviously roll the thing thin, a controller which makes them either squeeze it tighter or less tight to make the thing thicker or thinner, processor unit controlling it, and a radiation source with a detector above it. And obviously the radiation goes through the thin material that's being developed. Now hopefully this animation will show us through it. So this is how we use it. We have the roller for the material, a control unit to squeeze these rollers closer or to separate them so that it's thinner or thicker, beta source in this case, okay, it's a beta source, and a detector here, okay. And if we play it, we've got the rolling rollers, and the material comes through here and is rolled thin to a certain thickness. As you can see with the beta particles emitted from the source, they're passing through this material, some are absorbed and some pass through. Okay, so phase 2, if the paper becomes too thick, less radiation will be detected. So less will pass through, as you can see, because the paper's too thick. It's going to have an effect on the beta. It doesn't absorb beta completely, that's alpha, but it will make a difference to how much beta can pass through the paper. And the thicker it gets, the less beta can get through. So what happens then is the detector recognizes it's not getting enough intensity of beta radiations, so it will inform the control unit to squeeze the rollers closer together and therefore to make the paper thinner. And they will squeeze together, the paper will become thinner, and more beta particles will pass through until it's reached its measured thickness, and it will carry on like that. Similarly, if the paper becomes too thin, not enough radiation, too much radiation will be detected, and the detector sends a signal to the control unit telling it basically you're squeezing too tightly, move apart, because we're getting too much gamma getting through. Okay, oops, there we go. So again, too thin, we get too much gamma going through, and therefore the signal is sent from the detector to tell the control unit to move the rollers further apart until just the required and predetermined amount of beta gets through on this. Okay, so method used in manufactures plastics, paper, anything that comes out as a thick sheet of something or a thin sheet of something might use this method for quality control. But again, beta will work through some of these things, and the question might be, why not alpha? Why not gamma? Okay, so as I just said, here's an activity. This is a question that appears. Why a beta source is used, not alpha or gamma. Explain why how the detector regulates the thickness of the paper. So again, pause the video, answer the questions, jot down your thoughts, and let's see what you got with a model answer in a minute. Okay, hopefully we're ready for some model answers, and let's see what they might be. So first of all, why beta is used. Beta can penetrate paper, aluminium, thin aluminium, and other materials, but alpha wouldn't penetrate the paper at all. And gamma radiation would pass through it easily without being affected. So if you had a gamma source, the paper thickness wouldn't really make any difference to it at all. Hence the reason why beta is the correct source for this one. Explain how the detector regulates the thickness. Well, that's about the rollers. It detects the rate at which the beta passes through the paper. It affects the count rate. The count rate tells the processor, and the processor controls the squeezing of the rollers, either thicker or thinner, to change the thickness of the paper. Okay, so those are the sort of two common things that are assessed about using radiation and thickness checking. Smoke detectors, these are the things that hopefully you've all got in your houses. And these ones use radioactivity. So this is where you should have an americium 241 source somewhere in your house. And if you haven't, I hope you've got something similar, because obviously, you know, everyone needs to be safe, and smoke detectors are really important for this one. Now, they contain a weak source of alpha radiation, and as we know, or we should know, alpha particles are highly ionizing. So we have an alpha source here. There's our little alpha particles, 2 protons, 2 neutrons, a helium nucleus. They will ionize the air. They will break down the air, the molecules and atoms in the air, into ions. And the ions, being charged negative or positive, can therefore move. And if you use a battery, and you know the sort of special type of batteries that they have in smoke alarms, 9-volt batteries. 9 volts is a bit higher than most normal batteries. They're about 1.5, but 9-volt battery for this one. And it contains a potential of plus and a minus between 2 plates, basically. And these ionized particles caused by the alpha can actually then move. And as the charged particle moves either positive to the negatives and negative to the positive, that's effectively a flow of electric current. And the flow of electric current keeps happy, basically keeps the alarm off, because there's an electric current of ionized particles flowing between these plates. However, when smoke particles, which are tiny microscopic bits of soot, really bits of carbon, when they get here, they kind of get in the way, and they actually sort of reduce the amount of ionization that occurs, because they're actually affecting the movement of the alpha particles. They're being affected by the alpha particles. They're blocking the alpha particles, which are big and heavy, and crash into them. And therefore there's less ionization. So there's less ionization when smoke suddenly gets introduced to this one. And because there's less ionization, there's less current flowing between the 2 plates. And the detector in the alarm says, oh, there's not enough current here. Something is stopping that. It must be smoke. And the alarm goes off and keeps us safe. So in the diagram sheets I've sent out to you, you've got this diagram. And you need to be able to label to show how it works. Again, we've got our battery, 9-volt battery. We've got our positive and negative plates, because that's what the battery's connected to. And we've got the alpha source here. Okay, americium 241 is a source of alpha particles. And the alpha particles are emitted from here, as we saw in the cloud chamber, and ionize the air, creating these ionized particles, which are negative or positive, because it just bumps the electrons off them. They ionize the air, and the air then can conduct electricity. You've all seen sparks. Well, it's a kind of similar idea. Electricity can pass through ions in the air, and there's a current therefore flowing between positive to negative and negative to positive. So the detector recognizes there's a current going on there, and therefore keeps the alarm off. Smoke, though, as we see from the shading, will slow down the alpha particles, interfere with them. It will prevent much ionization taking place, and therefore the current, the amount of ions moving between these 2 plates, reduces. There's less current, and therefore the detector recognizes there's less current. Therefore, I'll sound the alarm, and everyone can wake up in the middle of the night and check there's no fire, and test the smoke alarm, or get out of the house quickly. So, a couple of things to think about with that. You need to, again, label your diagram for that, know how the components are, what the components are, how it works, and it's an alpha source. And think about the fact, you know, it's a radioactive source in our house. Why why is that, is it safe to have that in our house? But if you think about the properties of alpha particles that we know about, and also where we usually have our smoke detectors, hopefully you could come up with a sort of reasonable 2-mark explanation of why is it safe to have an alpha particle source in smoke detectors in our houses where we live all the time. Okay. If you can safely, and it's got to be safe, everything's got to be safe, but if you can, you've got access, and you can, without damaging it or yourself, have a look inside a smoke alarm if you never have before. You should see the radiation warning sign, which is this shape, stamped into the metal container. There'll be the battery, there'll be a little plastic siren, and there'll also be the metal container with that in. So, if you can safely, if you're interested to do so, have a look inside one and see, okay, yeah, I've got an americium alpha source in my house, in my smoke alarms. Okay then, so hopefully we've got to the point after this session of working through, and we can give these things, we've hit these objectives. Detailed descriptions of how it's used in applications. Again, I've sent the diagrams out. Understand why it's used in sterilising surgical equipment, irradiating food, etc, 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 and all the stuff we talked about. And in the manufacturing and engineering field, how does it work there? Okay, because radioactivity has a lot of really important uses in everyday life. Medical uses are a separate topic, and that'll be the next lesson. To finish with then, I've sent some activity homework sheets out for you to do as well, you'll be thrilled about. But also, these are true or false statements for this. So pause the video and just jot down 1 to 10, true or false do you think? And when you've done that, unpause the video and have a look at the answers. Okay, so pause the video, do your trues or falses, and then when you're ready, unpause it. And these are the answers. Yes, radiotherapy kills cancer cells. Next lesson topic. Food preservation? Yes, we've said so. Surgical equipment? Yes. Cleaning teeth? Better not be. Okay, we've got other things for those. It would be very dangerous in the mouth. Quality control? Yes. Crack detection in welding. Radio tracers? Detecting leaks in pipes? Yes, that's true. Radio tracers for medical scans? Yes. And we'll explore that next lesson. Smoke detectors, as we've just seen. Prenatal scans? No, we would not want to scan unborn babies with ionizing radiation for hopefully obvious reasons. We use ultrasound for that, don't we? And measuring the height of babies, again, any sort of ionizing radiation, nuclear radiation near people is not a good idea. Okay, so hope that was a useful run through of what we need to know. Hopefully you've got some notes, answered some questions, followed it up on the pages in the textbook, and have found this to be a useful activity. Okay, we'll have a Teams tutorial or office hours session for you to get back to me at some stage in the near future if there's concerns or questions or things you want to raise about this. But in the meantime, thanks very much.